Let us talk about dynamic modulus of asphalt concrete. So at the beginning, I will show you a profile of a pavement. The surface layer is asphalt concrete, then aggregate base layer, then aggregate sub base layer, and finally subgrade layer. So if we apply load, there will be some deformation, cracking in asphalt layer. So to design the pavement, the primary input parameter for asphalt layer is dynamic modulus. What is that? Dynamic modulus. We express it by E star. So dynamic modulus, what is that? We will go there. But why do we need this? We need this to calculate the deformation in this layer, any kind of deformation in this layer, whether recoverable or irrecoverable, that is permanent, whatever. So we need to know dynamic modulus to calculate deformation, and also we need dynamic modulus to calculate any kind of cracking. Any kind of cracking, like by any kind of cracking, I means like alligator cracking, top down cracking, bottom up cracking. These are the main cracking, or even temperature or thermal cracking also. So we need to have dynamic modulus to calculate any kind of deformation and any kind of cracking. So this is why dynamic modulus is the primary input parameter while designing pavement. So now we will see what is dynamic modulus. So dynamic modulus is again similar to Young's modulus. It is the ratio of stress and strain, ratio of stress over strain. But this stress or this strain is cyclic. We apply dynamic load. What kind of load do we apply? We apply, say, okay. So this is our applied stress, and the resulting strain will be like this. So if we apply stress strain on a cylindrical sample, say this is our sample, if we apply load, then we take the peak stress divided by peak strain is dynamic modulus. So in this test, we apply dynamic load, a sinusoidal load, and the resulting strain, we measure it. You can see there is a gap between these two. This gap is called phase lag. Phase lag. Why there is a gap or why there is a lag? Because asphalt concrete is a viscoelastic material. You know that in viscoelastic material, if we apply some load, it takes some time to deform. That lag is called phase lag. So whenever we will apply stress, it will not deform or it will not create strain instantly. It will create strain after some times. That is called phase lag. So, okay, so hopefully you understood the definition of dynamic modulus. It is a modulus but due to dynamic load. What kind of load? Sinusoidal load. Sinusoidal and only one phase. Again, something else also. We do not apply the compression phase. Sorry, the tension phase. We apply only compression. That means this is our sample. We apply load, take it out, load, take it out, load, take it out. We do not pull it. That is the other side. So this is compression. If I write somewhere compression load. So only compression part of the sine curve. Okay, then other question is, why do we apply this kind of load? The reason is, say our material is somewhere here. When this traffic will come and goes, it goes very fast. So the load applied on this material is similar to this, not exactly, but very similar. And we cannot apply any static or any monolithic load. The reason is, sorry, not monolithic, monotonic load. That means you will apply some load, applying. Not, we cannot do that. Here, my load application is very fast. So comes goes. So this is why we apply this kind of load. Something else also. What is that? Okay, then what are the type of sample we use? At the beginning, we mix the asphalt and aggregate, then compact it and prepare a cylindrical sample. From a cylindrical sample, we cut a sample like this. So this height is should be 150 millimeter, and this diameter is 100 millimeter. 100 millimeter. That means 4 inch over and height is 6 inch. We take this kind of sample and then we place it inside a chamber. So this is my sample. We place inside a chamber where we can control the temperature. Now, why do we need to control temperature? Because the temperature of asphalt like changes every moment in our real field. That is number one. Number two, the property or the modulus of asphalt concrete changes with temperature. So we need to know the we need to apply the exact temperature we want. And something else is that our traffic can go very slow, it can go very fast. So the application time of the load is also important, or simply frequency. Frequency means number of load per second. How many number of load we will apply per second. So frequency also matters. So temperature, if I write here, so temperature matters and frequency of load also matters. So what we do, we apply 5 different kinds of temperature. If I can remember correctly, 14, 40, 70, 110. If I forgot, let me check. So yes, these temperatures are in Fahrenheit. Yes, 40, 14, 70, 100, 130. So it is 100, then 130 Fahrenheit. So we test at 5 different temperatures and frequencies, 6 different frequencies. What are those? 0.1, 0.5, then 1, then 5, then 10, then 25. Is it 6? 1, 2, 3, 4, 5, 6. Yeah, 6 frequencies and 5 temperature. That is the standard. Now other question, why different frequencies? I already answered. My traffic may go very slowly, may go very fast. So to account different kinds of load application, we apply the sinusoidal load on this sample at 6 frequencies. At every temperature, every of these 5 temperature, 14, 40, 70, 100, 130 degree Fahrenheit. Okay, so hopefully you understood this now. After testing, what we do? For every case, we take the peak stress and peak strain, divide by this, and then we get the dynamic modulus. Dynamic modulus. So if I plot it, how it will look? So this is my dynamic modulus. So this is 0.1 hours, 0.5, 1, 5, 10, 25. Then say first we are doing 130 degree. So one value here, other value here, other here. Say this value at 130 degree Fahrenheit. Then for other temperatures, say 100 will be somewhere here. This is 100 degree Fahrenheit. Then this way 70 will be here, somewhere here. Then 40 will be here. this will be 40 degree Fahrenheit, 70 degree Fahrenheit, and then 14 will be somewhere here, 14 degree Fahrenheit. So these are the, now this is not linear, it is curved. Yes, but this is not linear, I did linear. I did almost linear, but again this is not linear. So something to observe, as the frequency, and this unit is hertz. Hertz means cycles per second. So as the frequency is increasing, my dynamic modulus is increasing. That is something to observe. So this way, if I go this way, it is increasing. Second thing, in this way, as my temperature is decreasing, it is increasing. So this way also it is increasing. So something to learn, as my frequency of load increases, my dynamic modulus increases. As my temperature is decreasing, my dynamic modulus is increasing. So this is something to know or understand. In summary, the dynamic modulus of concrete is not a constant number. It's not similar to steel or concrete. Modulus of steel or concrete is like very constant, very close to constant at least. But for asphalt, it is not constant value. It changes with frequency of loading and temperature. So in your road, if the traffic goes slow, the modulus is on. If the traffic goes very fast, the modulus is different. So that is something to understand. Okay, so something else also. You can see that this test is very costly in terms of preparation and costly equipment and like execution of everything. It takes like time and money, both cases. So sometimes if we cannot do this test, we have some empirical equation. One is Witzak viscosity based model, and other equation is shear modulus based model. Model means, so there are many equations, but two equations are very popular. One is Witzak viscosity based model, other one is shear modulus based model. It is in your book, very long equation. In that equation, here, if we know the viscosity of the asphalt binder and the gradation of the aggregate, and then we can find the modulus at different frequencies. Same thing, if we know the shear modulus, of asphalt binder and the gradation of the aggregate, we can find the E star. So we can use this equation to find E star if we do not have this sophisticated equipment. So hopefully you got an idea about dynamic modulus of asphalt concrete. If I summarize, it is a modulus due to dynamic load. We apply sinusoidal load, only compression, and measure apply the stress, measure the strain, and the ratio of peak stress divided by peak strain is the modulus. We do this test at 5 temperature, 6 frequencies. Why 5 temperature? Because we try to cover whatever the temperature may come to our real pavement, and the modulus of asphalt concrete is very dependent on the temperature. And why frequencies? Because the modulus of asphalt concrete also changes with frequencies of load. So this is why we try to cover different kinds of frequencies. And then after this we plot it, and then when we design pavement, we need to input this value. In the software. And something else, if we do not have it, or if we do not have this equipment, or like it is a lot of time. So what we do, we can use two equations. One is Witzak viscosity based model, other one is shear modulus based model. These are the two popular equations we can use to calculate E star. Okay, so today up to this, in next video we will see another property of asphalt concrete.